So 11.2, we're going to be talking about series. So remember, a series is the sum of a sequence. So in this first example, imagine we had the sequence that was given by the general term, a sub n equals n. Well, that would be the sequence 1, 2, 3, 4, 5 on forever. Well, what if we tried to add up all of the members of that sequence? So in other words, well, what is the sum of 1 plus 2 plus 3 plus dot, dot, dot? Well, turns out it can be difficult to add up an infinite series. So we're going to ask ourselves a simpler question, which is about partial sums. So a partial sum is the sum of the first n terms of a series. So if we take a look at our series that we have above, S sub 1 would just be 1. S sub 2 would be 1 plus 2, which gives us 3. S sub 3 would be 1 plus 2 plus 3, which would be 6. And S sub 4 would be 1 plus 2 plus 3 plus 4, which would be 10, and so forth. So if we look at our partial sums, so S1, S2, S3, S4, this forms a new sequence. Called the sequence of partial sums. So it turns out that, like we were talking about last time, we can find a pattern for this sequence of partial sums. So S sub n is n times n plus 1 divided by 2. And that would generate the sequence 1, 3, 6, 10, and so forth. So now, if we take the limit as n goes to infinity of S sub n, well, that's infinity times infinity divided by 2, so that's going to be infinity. So the sequence of partial sums diverges. So the series also diverges. All right. Let's take a look at our next example. So what is the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 on forever? Well, if we do the same thing, we make our sequence of partial sums. S sub 1 is going to be 1/2. And then S sub 2 is going to be 1/2 plus 1/4. So 1/2 is 2/4. 2/4 plus 1/4 is 3/4. S sub 3 is 1/2 plus 1/4 plus 1/8, which is, when we know 1/2 plus 1/4 is 3/4. 3/4 plus 1/8, well, 3/4 is 6/8 plus 1/8 is 7/8. And S sub 4 is going to be 1/2 plus 1/4 plus 1/8 plus 1/16 is equal to 7/8 plus 1/16. So 14/16 plus 1/16 is 15/16. So we get, those are the first 4 sequence members of our sequence of partial sums. So let's take a look at them. So 1/2, 3/4, 7/8, 15/16, and so forth. And we're looking for a pattern. So inside of this, we have our S sub n. It looks like our denominator is 2, 4, 8, 16. So that's the powers of 2. It's doubling each time. And the numerator is always 1 less. So that's going to be 2 to the n minus 1. So then S sub n is equal to 2 to the n minus 1 divided by 2 to the n. Now we can test if this converges. We can do a little algebra. So this is equivalent to 2 to the n over 2 to the n minus 1 over 2 to the n, which is 1 minus 1 over 2 to the n. If we take the limit as n goes to infinity of our sequence of partial sums, that's the same as the limit as n goes to infinity of 1 minus 1 over 2 to the n. Well, 1 over 2 to the n is 1 over infinity, so that's going to go to 0. So 1 take away 0 gives us 1. So all right, so in these last 2 examples, we were talking about the convergence of a sequence of partial sums. So let's formalize that up a little bit. And we say, if the sequence of partial sums, so S sub n equals the sum as n goes from 1 to infinity equals S, then we say the series converges. To S, and we write A1 plus A2 plus A3 plus all the way out is equal to S. Or, in sigma notation, the sum as n goes from 1 to infinity of the A sub n's is equal to S. The number S is called the sum of the series if the sequence of partial sums diverges we say the series diverges. All right, so now we're going to transition to geometric series. So a sequence is geometric if each term is the product of the previous term and the common ratio r. So in our set notation, that's A, AR, AR squared, on forever. And the general term, A sub n, then is A times R to the n minus 1. So if we suppose that R does not equal to 1, we can then write out our partial sum as follows. So S sub n, the nth partial sum, would be A plus AR squared plus all the way out plus AR to the n minus 3 plus AR to the n minus 2 plus AR to the n minus 1. So now this is an equation. So if we were to multiply both sides of this equation by r, the common ratio, we would have r times Sn. And if I multiplied everything on the right by r, it's going to increase the exponent by 1 on all of the r's. So a times r would become AR. AR times r would be AR squared, plus all the way out, we would have AR to the n minus 3 plus AR to the n minus 2 plus AR to the n minus 1, but then AR to the n minus 1 times r, negative 1 plus 1 is going to give us plus AR to the n. So now we have two equations. If I were to subtract these two equations from each other, on the left-hand side, we would get Sn minus r times Sn. And on the right-hand side, since we're subtracting, the first term doesn't pair up with anything, but the second term, the third term, in fact, all of them will pair up with something and reduce out to 0, except the first term and the very last term. So now I can solve this equation for S sub n by factoring out S sub n. I get S sub n times 1 minus r is equal to, factoring out an a over here, 1 minus r to the n. And then I divide by 1 minus r, and I divide by 1 minus r, and that gives me that S sub n is equal to a times 1 minus r raised to the nth power, all divided by 1 minus r. So this gives us a formula for the partial sums of a geometric series. And then this raises the question, so question, for what values of r does Sn converge? So we need to take the limit as n goes to infinity of Sn, which is the limit as n goes to infinity of a times 1 minus r to the n all over 1 minus r. Well, n is the only thing that's changing, so the a and the 1 minus r can come out of our limit, and we're left with 1 minus r to the n. So this limit is only going to converge, well, the 1's always going to converge, it really only depends on r. So this limit converges when the absolute value of r is less than 1. Because the absolute value of r raised to the n goes to 0 as n goes to infinity. So if we were to do that, then that would give us then that the sum is equal to, well, this would be 1 minus 0. We get a over 1 minus r, which is the formula for the sum of an infinite geometric series. So S infinity, or just S, is equal to a over 1 minus r, where the absolute value of r must be less than 1. All right, so let's go ahead and take a look at our couple of examples. So we wish to determine the sum of this series. So we have 7 minus 14 over 3 plus 28 over 9 minus 56 over 27. So we want this to be geometric, so we have an is equal to a1 times r to the n minus 1. So our first term, our a1, is going to be 7. To find our common ratio r, we divide a2 by a1. So that's going to be negative 14 over 3 divided by 7, or 7 over 1. So that's going to be negative 14 over 3 times 1 over 7. Those reduce, giving us a 2, and we get negative 2 thirds. So then, if we know our a1 and we know our r is 2 thirds, S infinity was a divided by 1 minus r. So it's going to be 7 divided by 1 minus a negative 2 thirds, which is going to give us 7 all over. The minus minus gives us a plus plus. So 1 plus 2 thirds gives us 5 thirds. So then 7 over 1 times the reciprocal 3 over 5 is 21 over 5. So the sum of 7 minus 14 over 3 plus 28 over 9 minus 56 over 27 is 21 over 5. All right, so to calculate this infinite sum, our first term, a1, is just going to be 6. Our r is a2 divided by a1, so 2 over 6, which reduces to 1/3. So then our S infinity is going to be a over 1 minus r, which is 6 over 1 minus 1/3. And this is technically a compound fraction, so we can just multiply the top and the bottom by the LCD of 3. So 6 times 3 is 18, and then that would give us 3 minus 1 when we distribute the 3 in. So that's 18 over 3 minus 1 is 2, and we should get 9. And if you did 1 minus 1/3 is 2/3, and then multiplied by the reciprocal, you get exactly the same thing, right? So it's just two different ways to accomplish the same task. All right. So now, example 4. We want to determine A1 and R and determine if this series converges. So at first glance, this kind of looks like a mess, right? So if we want to find A1, we don't really need to look any further than this. So A sub n is whatever that mess is, right? So 3 to the 2n plus 1 times negative 4 to the 2 minus n. And I'm going to do this two different ways to illustrate some different techniques. So to find A sub 1, what do I need to put in for n? Just 1, right? So if I put in n equals 1, A sub 1 is going to be 3 raised to the 2 times 1 plus 1 times negative 4 to the 2 minus 1. So 2 times 1 is 2 plus 1 is 3, so that's 3 cubed times negative 4, because 2 minus 1 is 1. 3 cubed is 27, and 27 times negative 4 is negative 108, if I did my arithmetic correctly. So that gives me A1. To find A2, I would just put in n equals 2. So A2 would be 3 raised to the 2 times 2 plus 1 times negative 4 to the 2 minus 2. Well, 2 times 2 is 4 plus 1 is 5, so that's 3 to the 5th times negative 4, and 2 minus 2 is 0. So then let's see. 3 to the 5th is 3 times 3 is 9, times 3 is 27, times 3 is 81. Times 3 is 243, and anything to the 0 power is 1. So now I have A1 and A2, so R is equal to A2 divided by A1, so that's 243 divided by negative 108. I go 243 all over negative 108, and I press enter, I get negative 9 over 4. So then, at this point, I notice that we have negative 9 over 4, and we know that for our series to converge, it converges only if the absolute value of r is less than 1. Well, the absolute value of r is equal to the absolute value of negative 9 over 4, which is 9/4. So the series diverges. And that will give us that it diverges. So I mentioned that I was going to do this another way. So if I were to approach this in a more algebraic fashion, I could start manipulating this algebraically. So we know that for a geometric sequence, we have the form an is equal to a1 times r raised to the n minus 1. Well, if I could write the left-hand side like the right-hand side, I would then be able to identify a1 and r. So using some properties of algebra, I could write this as 3 raised to the 2n times 3 times negative 4 squared times negative 4 to the negative n. And that's just using my exponent rules backwards. So then I could combine a couple of things together. So I have a 3 and a negative 4 squared. So negative 4 squared is 16, and 16 times 3 is going to give me 48. Then I can focus on this piece right here. I have 3 to the 2n. I could write that as 3 squared raised to the n times, and then I'm missing a minus sign there, this to the negative n. And if I move that from the numerator into the denominator because of the negative exponent, it would become negative 4 to the n. So we keep simplifying. I have 48 times 3 squared is 9 to the n divided by negative 4 to the n. So then that's going to be negative 4 to the n, which if I really wanted to, I could leave it like this. So now finally, we're ready for the last step. I can write that as 48 times negative 9 over 4 raised to the n. So I'm getting really, really close to this, but it's not quite right yet because my exponent's an n, but what I really want is an n minus 1. So I can write that as 48 times negative 9 over 4 times negative 9 over 4 to the n minus 1. Because now these two things have the same base. If I add them up, I will get this. So then finally, 4 goes into 48 12 times. 12 times negative 9 finally gives me negative 108 times negative 9 over 4 raised to the n minus 1. So after doing a whole bunch of algebraic gymnastics, I can compare that with an is equal to a1 times r raised to the n minus 1. So this would suggest then that my a1 value is negative 108 and that my r value is negative 9/4. Well, that's exactly the same thing we got up here using just the definition of the sequence. So you'll see this done both ways, and if you watch the video they put inside WebAssign, they're going to do it the second way. They're just making that process a lot harder than it needs to be for some unknown reason. So if you want to do it that way, it's fine. There's nothing wrong with it, but it's a bunch of extraneous algebra that's not making our life any easier. All right, so let's keep going. So our next example is we wish to write the following repeating decimal as the ratio of two integers. So in this we have 2.3 and then 17171717 repeating. So we can break it up into its repeating and its non-repeating part. So the non-repeating part of this is 2.3 plus the repeating part of this is going to be 0.017 repeating. And we want to write this as the ratio of two integers or as a rational number, or also known as a fraction. So the way we're going to do this then is we want to focus on the part that repeats. So we need to write each of these as fractions. So we have the 2.3, so that's 2.3, so 3/10. So this is going to be 23 over 10 plus, for this next part, we want the repeating part of this to be right next to the decimal. So we're going to write it as 1/10 times 0.171717 repeating, because if we do that, this will represent that repeating part on forever. So now we really want to focus on this bit right here. So we have two digits that repeat. So if we focus on that, we can write this whole part in here as 0.17 plus, but then if I don't want to change the 0.17, I would have to add some zeros, so 0.0017 plus, now I don't want to change that second group, so this part right here, so I have to add a couple of zeros, and now to get to the third group out here, I'd have to add 1, 2, 3, 4 zeros. So each time, it's the number of digits that are repeating that we're missing. And if I did that forever and ever and ever and ever, this would add up to 0.1717171717. Well, this then is A1, A2, A3, and I want to sum all of these up. So then, to use our formula, we have to know A1, that's the easy one, so 0.17 or 17 over 100, and we need to know R. Well, R is A2 divided by A1, which is 0.0017 divided by 0.17. And if we divide that out, we have 0.0017 divided by 0.17, and that's going to be 1/100th. So then our formula for that part, our S infinity, is A1, which is 17 over 100, all over 1 minus R, which is 1 over 100. Our LCD of all of our fractions is 100, so we multiply the top and the bottom by 100. In the top, they cancel out. In the bottom, when we distribute it in, we get 17 over 100 minus 1. So we get 17 over 999. So that right here is this part. So bringing everything down, we had 23 over 10 plus 1 over 10. So we had our 23 over 10 plus 1 over 10. And then we just found that our repeating part was 17 over 999. So then we get 23 over 10 plus 17 over 9990. And we'll finish that up on our calculator. So we go 23 over 10 plus 17 over 999, or 9,990 rather, and we hit enter and we get our reduced fraction. for this. So that is our fraction that represents that repeating decimal. And we can check that by just doing the actual division on our calculator or just asking for the decimal approximation. And we get okay, we've got to go back because I have a typo because I'm a crazy person. So, yeah, you're absolutely correct. 100 take away 1 is not 999. What should it have been? 99? So then, if we put in the correct digits and try that again, we get 1,147 over 495, which is then the actual correct solution. And if we approximate that using our decimal, we actually get back what we're supposed to. So, yeah, it should have been 17 over 100 take away 1 is 99, not 999. So, yeah, I don't know what happened there. Brain glitch. Okay. So now, let's go ahead and have you guys work on your U-try. So we start writing out a couple terms. So if we write out our first sequence number, A1 is going to be 0.123, and A2 is going to be 0.000123, and our R is going to be A2 divided by A1, so 0.000123 divided by 0.123 is going to give us that R is 0.001. So then, our formula for S infinity is A over 1 minus R. So we have 0.123 over 1 minus 0.001, which is 0.123 over 0.999. So if we multiply both the top and the bottom by 1,000 to move our decimal over 3 times, that's 123 over 999. Each of those are divisible by 3, so that reduces to 41 over 333. And if we check that on our calculator, 41 divided by 333 indeed gives us the repeating decimal 0.123123123, and so forth. All right, very good. Well, let's go to our next example, which is a telescopic or telescoping series. So sometimes we can find the sum of a telescopic series by using different algebraic techniques. So in this case, the idea of a telescoping series is that when we start writing out some terms, if we do the right algebra, we're going to get a whole bunch of things that reduce out. So by partial fraction decomposition, we have 1 over n times n plus 1 is equal to a over n plus b over n plus 1. And if we clear our fractions by multiplying by n times n plus 1, so n and n plus 1, n and n plus 1, and n plus 1, then here everything reduces out. Here the n's reduce out, and in the second term the n plus 1's reduce out, and we're left with 1 equals 2a times n plus 1 plus b times n. If we open our parentheses by distributing, we get an plus a plus bn. And then we regroup our n's together, so we get 1 is equal to a plus b times n plus a. And that gives us the system of equations. A plus b has to equal to 0, and a has to be 1. Well, if a has to be 1, then b has to be negative 1. So that tells us then that 1 over n times n plus 1 is equal to 1 over n, and then b is negative, so minus 1 over n plus 1. So if we were to write out this series, so the sum as n goes from 1 to infinity of 1 over n minus, I'm getting ahead of myself. We should write out the original series first, which is 1 over n times n plus 1. This is the same as the sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1. So I've basically taken my an and rewritten it in a different way. So let's write out some of our partial sums using this new an. So S1 would be 1 over 1 minus 1 plus 1 is 2, 1 over 2. S sub 2 would be 1 over 1 minus 1 over 2 plus, now I put 2 in, 1 over 2 minus 2 plus 1 is 3. And my S sub 3 would be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. If I write out one more, S sub 4 is going to be those same first three terms. 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5. So as we write out more and more and more of these terms, we notice something interesting happening. So if I analyze this, the first one's kind of boring, but here I have a negative 1/2 and a positive 1/2. So they cross out. Here I have a negative and a positive and a negative and a positive. And then here, negative, positive, negative, positive, negative, positive. So looking for a pattern here, we have S sub 1 is 1 over 1 minus 1 over 2. S sub 2 is 1 over 1 minus 1 over 3. S sub 3 is 1 over 1 minus 1 over 4. And S sub 4 is 1 over 1 minus 1 over 5. So based on that pattern, we would guess that S sub n, well, 1 over 1 is 1 minus 1 over n plus 1. And if we check, if I put in 1, I get 1 minus 1/2. Okay, that's the first one. If I put in 2, that's 1 minus 2 plus 1 is 3 is a third. That's good. If I put in 3, I get 1 over 3 plus 1 is 4, so minus a fourth. And if I put in 4, 1 over 4 plus 1 is 1/5. So this shows that based on, after doing our partial fractions, that our partial sum is this. So if I take the limit as n goes to infinity of my sequence of partial sums, that limit is going to be 1. Because 1 divided by infinity goes to 0. So then this tells us that by telescoping, the sum as n goes from 1 to infinity of 1 over n times n plus 1 is equal to 1. All right. So now we want to talk about the harmonic series. So the harmonic series is special in the sense that it's a canonical example, which means we're going to use it for a lot, but we'll also see that it kind of acts as a borderline for something that we'll talk about a little bit later. So the harmonic series is the sum as n goes from 1 to infinity of 1 over n. So 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over n going on forever. So the first question we want to ask ourselves is, does this series converge? Well, to answer that question, we're going to analyze some partial sums. So let's consider the partial sum s sub 2 to the k. So to give an idea of what that is when k equals 1, that's going to be just s sub 2, because 2 to the first power is 2. So that's going to be 1 plus 1/2. And then when k equals 2, 2 squared is 4, so that's going to be s sub 4. So 1 plus 1/2 plus 1/3 plus 1/4, and we'll write out one more. So when k equals 3, that's going to be s sub, well, 2 cubed is 8, so that's going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 all the way out to an 1/8. So what we're going to notice is if I group these together in a certain way, the first thing I'm going to notice is that these two first terms are bigger than 1/2. Well, because 1 plus 1/2 is bigger than 1/2. Then if I look at these next two terms, well, 1/3 plus 1/4, that is bigger. So we know that 1/3 is bigger than 1/4. So then this is bigger than, since 1/3 is bigger than 1/4, this gives us that 1/3 plus 1/4 is bigger than or equal to 1/4 plus 1/4. And 1/4 plus 1/4 is 1/2. So then this is bigger than 1/2. So these two guys are bigger than 1/2. The first two terms were bigger than 1/2. And now if I look at these next ones, 1/5, 1/6, 1/7, and 1/8, Well, 1/5, 1/6, and 1/7 are all bigger than an eighth. And 1/8 plus 1/8 plus 1/8 plus 1/8 equals 4/8, which is a half. So then, since these are bigger, this whole group is also bigger than a half. So when we start analyzing our sequence of partial sums, we know that the sequence of partial sums s sub 2 to the k has to be greater than or equal to, well, for each k, it's going to be a half and a half and a half. So that's going to be 1/2 times n, which is n over 2. Sorry, k over 2.
Professor, is that the big?
All right, so we have s to the 2k, that subsequence, is greater than or equal to 1/2 times k, which is k over 2. So now if we take the limit as k goes to infinity of k divided by 2, this equals infinity. So this diverges. So if that limit diverges, then the series must also diverge. So we've just proven that the harmonic series, so the sum as n goes from 1 to infinity of 1 over n, diverges. So that's a good fact to know, and we're going to use that fact quite a bit later on. And we'll talk about this a little bit later in 11.3, that the harmonic series acts kind of as a border. And what I mean by that is there's a certain type of series called a p-series, where p-series on one side of this converge and p-series on the other side diverge. So the harmonic it doesn't converge, but it diverges very, very, very slowly. And that's kind of a strange concept, and we'll talk, like I said, more about that as we move on into some other sections. But we'll come back, and the harmonic is not going anywhere. All right, so the next theorem that we want to talk about is the test for divergence. So most of the time we want to know if a series converges. And we like it when they do, but quite often series, like we just saw, don't converge. And so the test for divergence can help us do that. So the test for divergence says if the limit of the ANs does not equal 0, then the series diverges. So basically, if we think about it in terms of, let's go back to our very first example, where we explicitly discovered that it didn't converge. But if you were going to add 1 plus 2 plus 3 plus ... on forever, is that ever going to get close to one number? Well, the answer is no, because if I just keep adding another bigger and bigger number, the sum is just going to keep getting bigger and bigger and bigger. So to give that some context, what the test for divergence says, if a series wants to have any chance to converge, then the limit of the sequence that makes up the series has to have limit 0. Because essentially the idea is if we want it to converge to a number, what the sequence is converging to has to be 0. Because if we just kept adding 1 and 1 and 1 and 1 over and over and over again, there's no way that that series could converge. The harmonic series also shows us that the converse of that is not true. Because what's the limit as n goes to infinity of 1 over n? 0. And just because the limit as n goes to infinity of 1 over n equals 0, it doesn't mean a series converges. So we have to be a little careful with that for our test for divergence. This tells us if a series diverges only. If the limit as n goes to infinity of an equals 0, this test doesn't tell us anything. It could converge or it could diverge, but it doesn't tell us anything. It only tests for divergence. All right, so let's go ahead and do an example. So we take a look at the sum as n goes from 1 to infinity of 3n cubed minus 5 over n cubed plus 1. So this is going to be our a sub n. And if we want to take the limit as n goes to infinity of our a sub n, that's the limit as n goes to infinity of 3n cubed minus 5 all over n cubed plus 1. So if we factor out our the degree of the denominator from both the numerator and denominator, so they're cubed, so that gives us n cubed times 3, sorry, not plus, it's a minus 5 over n cubed divided by, we factor the n cubed out of the denominator, we get 1 over 1 plus n cubed. Our n cubes reduce out, and now when we take the limit, a constant divided by infinity is 0, and the constant divided by infinity is 0, so our limit converges to 3 over 1, which gives us 3. So by the test for divergence, the series diverges. So our theorem said if we take this limit as n goes to infinity, and if it's not 0, then the series diverges. So we took the limit of the a sub n's, and in this case we got 3, which means then that the series diverges. Because as n gets really, really big, what this is saying is we're essentially going to be just adding a number really, really close to 3 again and again and again. So 3 plus 3 plus 3 plus 3 plus 3. So that will diverge to infinity. All right. I believe we are at the grand finale for today. So all right, so in this U-tribe, we're going to want to use L'Hopital's rule. So if we're taking the limit as n goes to infinity of the sine of 1 over n divided by 1 over n, as n goes to infinity, 1 over n goes to 0, the sine of 0 is 0, and 1 over infinity is 0. So this is type 0 over 0. So we take the derivative, and this is going to be equal to the limit as n goes to infinity. The derivative of sine is cosine 1 over n. And then by the chain rule, we multiply by the derivative of the inside, which is negative 1 over n squared. And the derivative of 1 over n is negative 1 over n squared. So now these two guys reduce out. And cosine is a continuous function. So we can pass the limit inside our trig function, so the limit as n goes to infinity of 1 over n, and 1 over infinity is 0, so this converges to cosine 0, and the cosine of 0 is 1. So the value of our limit is 1, so by the test for divergence, the series diverges. So I just want to mention, so we just barely got started on this sheet. So you'll notice I mentioned that we're going to want to have this. It's got a summary of a couple of different things. So the first thing that we just talked about was the test for divergence. It's got its name, and then it has a quick summary of what it's going to be. So the rest of chapter 11, well, the next 6 sections in chapter 11 are going to be covering a whole bunch of different tests for series, and then on the back side we're going to talk about Maclaurin and Taylor series, and it's got some stuff there. So this is just a summary of a whole bunch of formulas, tests, and theorems that we're going to be using. So you're going to want to keep this sheet handy as we're working on some of these problems.